When you're driving down the highway, have you ever really thought about what's happening right under your wheels? I mean, not just the asphalt, but deep down in the ground. There is a whole world of invisible engineering at play, and it's the only thing keeping our roads from, well, collapsing. So let's peel back the pavement and see what's really going on. Okay, so just imagine this. A huge, fully loaded 20-ton truck comes roaring down the road. But just a few feet below the surface, there's a critical water main. What's stopping that pipe from getting crushed flat as a pancake? The answer isn't just, oh, it's a strong pipe. It's a really deep understanding of physics and a crucial engineering standard. To figure this out, engineers can't just guess. They need a benchmark, right? A common playbook they can all use to talk about these massive forces. And this is where we meet the unsung hero of our story, the H20 standard load. The H20 load is a standard that comes from AASHTO. That's a mouthful. It stands for the American Association of State Highway and Transportation Officials. But what it really is, it's a hypothetical worst-case scenario truck. Engineers pretend there's an axle carrying 32,000 pounds pushing down. They use this ghost truck to calculate the absolute maximum stress that anything buried under the road will ever have to face. And having this one standard is absolutely clutch. It means that whether a project is in Florida or Alaska, the engineers are all working from the same safety manual. It creates this universal language for keeping all that hidden infrastructure from failing on us. But here's the thing. That H20 load from our ghost truck, that's only half the story. See, under the ground, there's this constant battle happening between two totally different forces, the live load and the dead load. And understanding how these two duke it out, well, that's the key to everything. The best way to think about this is like a punch versus a blanket. The live load from traffic is like a quick, powerful punch. Bam! It's intense, but then it's over. The dead load, though, is like a heavy, weighted blanket made of soil and pavement. It's always there, just constantly pressing down. So digging into that live load, the punch, the most important thing to get is that it loses its steam really fast. Right up at the surface, it's incredibly powerful. But as that force travels down through the soil, it spreads out, kind of like ripples in a pond, and it gets way, way weaker. Now, the dead load, the blanket, is the complete opposite. This is the relentless, crushing weight of the earth itself. And it's super predictable. The deeper you bury a pipe, the more dirt is piled on top of it, and the heavier that blanket gets. More depth simply equals more pressure. Simple as that. So you've got this awesome dynamic, right? One force is the king of the surface, and the other is the king of the deep. This means that depth is the ultimate referee in this fight. And this is where it gets really, really cool, when you actually see it on a graph. All right, let's break this down. That vertical line on the side, that's our depth, how far underground we're going. The horizontal line on the bottom, that's pressure, how hard everything is squeezing. Now let's plot our two contenders on the chart and see who wins. First up, the dead load, our heavy blanket. And look at that. It's a perfect, straight, predictable line. No surprises here. Go down 1.8 meters, you get about 34 kilonewtons of pressure. Double the depth, and yep, you pretty much double the pressure. Simple and steady. Whoa. Okay, now for the live load. That punch from the truck. Right near the surface, it is an absolute monster. We're talking 96 kilonewtons per square meter. It totally dwarfs the dead load up top. This is the pipe killer, right here. But watch what happens as we go deeper. By the time that force gets all the way down to 3.6 meters, poof, it's almost gone. Down to just 6 kilonewtons per square meter. It's like the earth just absorbed the punch completely. And here it is. This is the big reveal. When you put both forces on the same graph, you see that perfect X, that crossover point. That is a magic spot. It's the exact depth where the constant, heavy blanket of the dead load officially becomes a bigger threat than the fading punch of the live load. So what does this all mean for an engineer? Well, it gives them this incredibly important rule of thumb. If you're working shallow, say less than 1.5 meters, you have to design for the punch from traffic. That's your number one enemy. But if you're going deep, more than 2 meters, forget the traffic. Your main problem is the crushing weight of the earth itself. Okay, this is all great in theory, but how does an engineer with a hard hat on the ground actually use this to build a safe road? Let's walk through a real-world decision to see how this graph turns into actual groundwork. All right, picture this. An engineer needs to install a pipe 2 meters down. So first, they calculate the dead load for that depth, the blanket. Then they look at the graph to find the live load, the punch. They add those two together to get the total pressure. Finally, a little bit of math converts that pressure into the specific force the pipe has to handle. That final number is what they take to go pipe shopping. And there it is, 39 kilonewtons per meter. Now that's not just some number on a spreadsheet. That is the pass-fail grade for this pipe. The pipe they choose absolutely has to be stronger than this or it's going to fail. No exceptions. So now the choice becomes crystal clear. The engineer just goes down the checklist. Can a Class 2 pipe handle 39? Nope, not even close. What about a Class 3? It's rated for 36. That's cutting it way too close for comfort. You never, ever want to be that near the limit. And there you have it. The math makes the decision for you. Only a Class 4 pipe, rated for about 48 kilonewtons per meter, gives you the strength you need plus a safe buffer. And just like that, an abstract graph leads directly to a real-world, safe installation. So, let's just boil this all down. What are the big takeaways? First, under every single road, there's a war going on between the punch of traffic and the blanket of soil. Second, depth is the critical factor that decides which one of those forces wins. And third, doing this math right is literally what keeps our hidden infrastructure from collapsing under our feet. It's pretty amazing when you stop to think about it. It kind of makes you look around and wonder, what other invisible calculations, what other hidden engineering standards are quietly working in the background right now just to keep our entire world from falling apart?